So today we are starting a new lecture, and that is the lecture on root finding. This is actually so far we have built our toolboxes, so to speak. We learned how to program or essentials of linear algebra and programming, which will enable us to actually create arrays and then actually do something with them with the numerical methods that we're going to start developing. And we also learned to analyze errors. What are the errors? Where can we expect them? Which ones we can avoid, and which ones we simply have to monitor and see how big they are. So this is one of the first actual topics that you will find helpful, or I hope you will find helpful. Root finding is essentially finding roots of an equation, and you need numerical methods when those equations are not simple. So for linear equations or quadratic equations, those we have formulas for, but there's a lot of problems where you don't have the formula. How many of you are in thermodynamics? Is Dr. DiCarlo asking you to program in MATLAB in that class? You will, or possibly even in. So thermodynamics is we actually had at the very beginning of our class, we had that example of Peng-Robinson equation and finding the roots of that equation. So this is a perfect example where you actually need to find roots. So it's something, I hope that the moment he poses you a question, that instead of going to tables, you will think of programming it in MATLAB. That is my hope. So think about it in thermodynamics. It's sort of the ideal candidate. This is not to say that there are no others. Okay? All right. So again, we went through the introductory parts on the fundamentals, and now we are ready to actually start using those fundamentals and solve something. So here's a fun root finding problem. Okay? Basically, we have two types of glasses, and you might be missing a beer glass here, but beer glass is not as interesting, I guess, geometrically. So we're gonna stick with martini glass and red wine glass, and we're gonna assume that this wine goblet is actually kind of part of a sphere, just to have a simple calculation. So we're wondering, what is the height up until I need to fill the glass to have certain desired volume? Okay. So volume of a spherical cap. This is a formula that is given. So if I have a sphere of radius r and I have this height h, then this a I can find from basically from the basic geometry in Pythagoras. I can figure out what h is, or a is. So basically, when I look at the volume, I get a formula of the volume that depends both on radius r that I know and h. Okay, so this is a simple math. We're not going to go into details. So let's just take, okay, volume of this cap is given by this formula. So I want this volume, okay, to be 216 times p over 3, okay? Because when I go out, I think in volumes in terms of p. Anyway, this is really just to cancel the p. It's like, dear waiter, please give me 216 over 3 times p milliliters of wine. I'll do that next time in a restaurant and see how it flies. So basically, what we really then need, we're asking ourselves, what is this height? Okay? So we will always translate an equation like this into an equation where I have the equation of interest equals to 0. Okay? And the reason we are doing that is that then all the problems are sort of presented in the same way, so I can actually apply the same algorithms to them. Okay? So that's why I'm looking at this as a root finding or a zeros finding for this equation. Now, cubic equation is not as simple as quadratic. There's actually some formulas that can give you this, but they're kind of lengthy. So this is actually one of the equations where I could possibly want to actually have a numerical method to find the zero of this equation. Okay. All right. Second one is the problem from second example. It's a problem from thermodynamics. already mentioned at the very beginning. So basically, I have a Peng-Robinson equation for the state of the thermodynamic state of real gases. Okay. So ideal gas is the one where PV is equal to RT. That is a linear relationship. I can figure out the moment I have T or P, I can figure out V. So basically, if I have 2 out of P, V, and T, I can find the third really easily. Okay. I can just plug it in. Now, in Peng-Robinson, okay, if I have P and T, finding V is not easy. Okay. So if I have V and T, I can find P all fine. But if I have P and T and I'm wondering what the volume is, well, then I'm in trouble. Because I cannot easily extract what V should be, VI should be in this relationship. Even when A and B is something that I have, it's again, these are again tabulated thermodynamic quantities. So the way I will pose this problem is, okay, I will give myself P and I will give myself T, and then I will plug them in and reformulate this equation as a function of V equals to 0. Okay? So this is now when I put P as 50 and T as 473, and this is already multiplied by R, the gas constant, then I will actually have 50 minus all of this is equal to 0. Okay? And now I have formulated it into a root finding problem, so I will apply that. We will learn the methods as we go. So basically, every problem, like I'm typically solving an equation, something is equal to something, I have to translate that equation into sort of a root finding form. Finally, there's another example of falling parachutist. Okay? So we know that Newton's law applies. Its integral version is that force is equal to mass times acceleration. Okay? Our force balance here is the drag force and the gravity force. So basically, by opening a parachute, I'm increasing the drag. And when the two balance themselves, parachutist starts falling with a constant speed without accelerating. Okay? So basically, I can put this mg minus c is the typically a coefficient that you can find from, or the whole point is actually to find it often, so I can, based on the coefficient known, I can know which parachute is better performing. Okay? So basically you form this, and when you integrate you will get that the V of t is gm over c times 1 minus e to the c minus m over t. Okay? So now if I actually have the data, so when I'm evaluating parachutes and I'm looking for the C, when you have the data, you can plug it in, okay? And you can see which C zeroes out this equation, okay, based on the measurements that you can make. So basically you will get f of C as this function with plugging in all of the values that you measured. So V and T are the things that you measure. So when you plug them in, you get that f of c is equal to 0, and that's how often one finds coefficients that are relevant in, this is an industrial product, right? So essentially, I can find c by finding the root of this nonlinear equation. All right, so these are our motivation problems. Now let's actually set up, so just as a recap, I have a lot of problems that come down to a quadratic equation or something that I have formula for. Those are great. That's not what we're studying here. We're here looking at the problems that are not so simple. So I gave 3 problems where there's no analytical or easy analytical solution. So we need to use a numerical method to solve. Every time you're using a numerical method, you will not find a precise solution. So you will be close, and you care to be close enough, and for most of the applications, being close within certain error is fine. Okay? So with numerical methods, you're always finding an approximate solution. All right, so this is the whole list. We will actually find out that finding roots of an equation it's not necessarily easy or given. Even if you have a numerical method, you don't know. Sometimes there's multiple roots, and you will be able to find one at a time. Okay? So basically, you might need to apply the problem multiple times. And it's not always straightforward to find that one. Sometimes these methods will actually fail. So this is the reason why we have multiple methods, so I have an array of options to try. So-called bracketing methods will be our first topic, and if you want to do reading, it's chapter 5 in our textbook. Okay? Those are graphical, bisection, and false position. And those methods are guaranteed to find a solution. The problem is you need to know the brackets where that solution is. Okay? And that's a finding of its own. So it's not necessarily easy. And then open methods just start from a given point. You give it a starting point and you let it go, and you're hoping it's going to find the root. Okay? So those are so-called open methods. Again, there are 3 that we're going to look into, and the corresponding chapter is chapter 6 in the textbook. We will not go. Polynomials are sort of a brand or a topic on their own. They're a whole separate, they're very specific in the way they look like, so they have very specific methods. So there's specialized methods for finding roots of polynomials. We will actually not focus on those. So everything we do, most of actually our problems will be polynomials because those are easy problems to come up with. If I'm just coming up with something, I'm going to be x to the 4 minus 3x to the 3 and so forth, right? So that's an easy example, so we will actually use a lot of polynomials, but there are separate methods that are addressing for finding all of the roots in polynomials, and we will not spend too much time on those because essentially the methods that we will cover, they apply to all functions and not necessarily polynomials. All right. So first and simplest method is a graphical method. So what do? You have an unknown function, and you're looking at where is it a 0. Well, first thing you do is you plot the function. Okay. So now, with MATLAB, we learned how to plot. In order to plot anything, I need a given set of points. I'm calling this C. Okay, so I need an array of C's. And then I need to compute F at those C's, and that's really easy in MATLAB. I just plot F. So let's do that. Okay? Give yourself an array of C's between 0 and 20, and plot F of C if F is given here on the screen. Let's go. So this could be, for instance, actually a very simple, small question on your exam. I give you C's, I give you a function. Write the MATLAB code that will plot that. So what is my choice for C's? 0 through 20? Sure. And I'm going to put at least 0.5 so I have some nice set of points. Let me actually make it really fine. I'm going to make my MATLAB work. Okay, so I'm going to do quite a bit of points. 400 as a matter of fact, 401. So how am I gonna find F? Can I write just 667.38 divided by C? Is that gonna work? No, I need vectorization, right? So I need that dot. So that will create a vector and go one by one value. And then I'm going to multiply that. 1 minus exponential of oh, it didn't complain. Okay. So I don't necessarily need dot multiply here because this is just a constant times entire array, so it works. And exponential of array works because exponential itself is vectorized. And I can also subtract a constant from the entire array, and it's going to do it element by element. Is this clear? So plot it is as simple as plot CF. Okay. And I'm going to set. Now, in order to actually, here's where 0 is, okay? So f is 0, where basically this 0 line intersects my function, correct? That's where my function is 0. If I was looking for function is equals to 5, then I would actually look where there's a function equal to 5. Now, how will I plot this? I can plot C's, and I can say first, hold on, and then I can plot C's and a 0 array of the same size, right? And that's gonna plot me a line where all of the y coordinate is 0. Whoops, and then I didn't have enough brackets. So here's the line. So my 0 is right where the two intersect. And this is essentially a graphical way to find this. If I was,
What is the
hold on, it basically adds this plot. So if I just did without hold on, it would change it to just that. Yes?
So that's basically you're just finding exactly where that function is equal to 0 for the value of C.
Yeah, graphical. Okay. Now, if I was up for like details, I would keep zooming in.
Can you do like an intersect function? Intersection of these two lines?
Just a second. So basically, I can zoom in, zoom in, zoom in. Okay. So it's somewhere between 14.77 and 14.775. Yes. Now, do I know the function of from the top of my head? But ultimately, this line is as fine for the. Let me do this. Okay, so I'm gonna put so you have to be aware. So these are now I actually have a star for every point that I created. So when I zoom in, okay. So when MATLAB plots your line, okay, the only information it really has has information at these points. In between, it plots a straight line. So technically, you could actually find this interval up close. And that's essentially what we will end up doing with our numerical methods. So essentially the function that would give you this intersect would essentially be your root finding method that we're going to go with. So geometrically, really, here, you know this, if you know this point and you know this point, you can approximate this with a line, okay? And line has a very simple linear description, right? And the line x is equal to 0 has a simple linear description, so you can find from intersection of two lines, that's an easy. Does that make sense? Because just because the plot looks smooth, that doesn't mean that you have points at every possible point. Right. So basically MATLAB, when it plots these yellow stars are the actual points, okay, they're calculated, but in between those, when it plots a line, it's just really connecting them with small straight lines. It's just that they're so small that your eyes are not going to see the difference. So essentially, when I'm actually looking at this, I can actually see, so all of the points here for the function, the values, the y values or the f values at all of these points are positive. Okay? And all of the points here are negative. So technically, if I know that, let's actually look at, so here for 14.4, I have a positive value of f. And for 15.1, I have a negative value of f. And my f is a continuous function in between those 2 points. I have to cross a 0 somewhere on that way. Okay? So the bracket, or finding a bracket, essentially means, oh, I can find a point where my f is positive, and I can find a point where my f is negative. And if f is a continuous function, then somewhere in between those two lines, I gotta hit the 0. If I'm going from positive values from negative to negative values, or from negative values to positive values. And that will be a key for the search for roots in these bracketing methods. Okay? Now, this is graphically, I can go and refine, and basically in my array of C's and F's, I can actually find these 2 points, okay? And I can get rather close. Okay? So if I just take a point that is halfway between these 2 points, and these are the 2 that I have in my arrays where I computed, okay? That's actually pretty close to 0. So that's actually what it means to look for things graphically. If I didn't have MATLAB and these advanced plotting tools, what you could do on paper is give yourself about 5 points, and here are the results for those 5. Okay, so that's actually there on the slides. So you can give yourself, evaluate at some reasonable range of something that you can quickly punch into the calculator to see if for C is equal to 4, F is 34, then 17, then 6, then minus 2, then minus 8. So essentially, I know that I gotta hit a 0 somewhere between 12 and 16. And once upon a time, or if you don't have anything else other than calculator, basically you can just kind of keep searching now in this and refine this further pretty much as much time as you have. Okay? So that's what engineers did. So if you have nothing else, you can actually resort to this. So my root is somewhere here, and that is the graphical point. So basically, just by having those 5 points, my root is somewhere between 12 and 16. I actually zoomed in, so we saw that it's somewhere between 14.7 and 14.8, roughly. And we can choose, this is actually a mathematical theorem, but if you have a real and continuous function, and you have one value that is positive and one that is negative, or you find 2 points where it's positive and negative, then you gotta hit a 0 in between. So mathematically, what we will actually, in our algorithm, we will look for this lower and upper x, xl, and xu, such that f of xl times f of xu is less than 0. That means that I have opposite sign. So either this one is positive and this one is negative, or the other way around. This one is negative, this one is positive. Yeah? So basically that means that I have a bracket, and I have a root somewhere in between XL and XU. Our first, so this is basically a graph that you can just zoom in on your screen, but that's essentially what I plot. And we had this function where f of c was positive, f of c is negative. I gotta hit a 0 somewhere in between. Okay. So the first method is inspired pretty much by trying to now do smart refinement of this interval. Okay. So I start with my bracket, or my interval XL, XU. That is where I know that f of XL times f of XU is less than 0, so they have opposite sign. Okay. And then I look at the half of that interval. Okay. So now half is my 14, right? Then I basically say, okay, what is my next interval? It should be either this interval or this interval. Which one it's obvious that it is? 14, 16, right? So from this plot, it's obvious that 14, 16 is the next interval that I should refine my search. So it's a smaller interval where I'm searching for that. How do I mathematically express that? What do I need to check for this interval to continue with it? I just told you what the rule for the bracket is. One endpoint, f of one endpoint times f of the other endpoint should be negative, right? So basically, I'm going to check what f of 14 is, and I'm going to check, is f of 12 times f of 14, is it a negative number? No. But this other one, f of 14 times f of 16, is a negative number, correct? Therefore, this is my next interval. Then I'm going to keep going. So now, my bracket, or the interval, is 14, 16. It's zoomed in right here. Okay? I'm going to look at the midpoint. Midpoint between the two is what? 15. It's right here. Okay? Then I'm going to check f of 15 times f of 14. Is it negative? Look at the values here. This is a 0, by the way. I'm zoomed in on that graph. You can actually look at it yourself on your computer. Yes, it is. So this is my bracket. So if f of my new point, 15 times f of 14 is less than 0, that's my bracket. Okay? So I'm going to zoom in here, and I can keep going like that. On this search, I'm going to pick 14.5 and 15, because I have a negative times positive number. And I can keep going until I find this close enough. The width of my interval is close enough. When is that? When I decide this. So these are those limits that, like in all of these searches, you're going to get close enough, or as close as you request and have time for. So in this case, it's going to be search, so it's going to be relatively fast, so you can keep going. But in often, if it takes a long time, you're not going to do that. Or if you have to repeat this 100,000 times for 100,000 points on your vlog, you're going to be not so picky about how close you get. Okay. So those are the certain. So you decide when to stop. So this is the algorithm. You have, or you know, the tool to program this. Let's go.
So is your answer going to be an interval, or is it going to be a point that you just like
You can report the midpoint of that interval or the endpoints, one of them. But I would report the midpoint. But if they're close enough, if the width is less than 10 to the minus 6, you're not even going to know it when you print the number. All right, so let's create the function. or a script. You can start with just having a script that basically programs that function f that we just plotted. Okay. You know that 12, 16 is a good starting bracket, so let's start with that. So this gives you an idea. You of course have to, so I would call your 12 and 16 XL and XU, and then have a loop that is going to keep replacing those lower and upper values of the interval based on these rules. There's actually an algorithm that is a little more amenable to programming right here. And then you and I can help as you have questions. I'm gonna stop the video so we don't have empty space in there.